Today we'll be solving the Leetcode question 23. Watch case ordered list. This is a Leetcode hard question. So you are basically given an array of k linked list. Okay, and each linked list is sorted in a ascending order. So 1 4 5 1 3 4. Then we have 2 6. Okay, and this is a list of list, we can say. And merge all the linked list into one sorted linked list and return it. Alright, so this is in the output. We have the sorted linked list. It is the combination of all three linked lists combined together. Okay, all right. So here we'll be looking into a simple approach. A simple approach will be a brute force approach. That what we'll do is basically, let's say there are three lists: 1 4 5, 1 4, and 2 6. So what we'll do is basically we'll traverse through each list one by one. Let's say can we consider first list, and then we'll maintain an array. Okay, and inside the array we'll basically store all the elements and the all the list. So we traverse the list and we'll store the elements. So 1 5 4 1 3 4 for the second list, and for the third list will 2 and 6, and then we'll apply sort function to basically sort it. And as simple as it sounds, but it's not actually very efficient because you have to travel all the lists. So obviously the traveling part will take O of n, right? We have to maintain a nodes list. We have to traverse the list, um, and we have to add all those nodes inside our array list, and then we have to sort it. So this will take O of n time complexity. This will take log n complexity. Sorry, n log n. And this also, again, we have to create a new linked list. So this is basically creating a list from the scratch. So this will again take O of n. So overall complexity for this will be O of n log n. And so this will be the time complexity, and the space complexity will be O of n. Alright, because we'll be storing where n is the total number of elements in all the key number of linked lists. Alright. So what if we want to improve the complexity of this? Alright, so one simple approach that a better approach we can say that we can do is to basically use the concept from the merge two sorted list. Okay, so let's say we have given only these two lists. So this list, the third list is not given, and we have just two lists. We have done this problem before, so while checking this, we basically check L1 and L2. We'll check if which is uh, so we'll also maintain dummy node, which will always point to the first element in the L1 or L2, and then we'll just we'll not store it or create a new linked list. Rather, we'll just rearrange the uh, existing nodes according to the order, ascending order. So we'll check L1 and L2. Let's say here both are same, so it doesn't matter. Let's say we'll consider so it will be one. Then the L1 pointer will move from here to the next element. Alright, that is 4. Then again the comparison will happen. Now this time L2 is smaller. So we'll add the L2's value. We'll move L2 to 3. We'll compare both L1 and L2. L2 is smaller, then we'll add 3. L2 will again move. So this is the basic concept of merge to carry sorted list. And then we'll add 4. L1 will move here. Then we'll add L2's value is 4 and then 5. So now we have merged these two lists and made a new list. And now this list will act as the L1 list, and the L3 list will act as an L2 list, and now we'll combine these two lists together. So we'll make a function for merging the two elements and we'll pass the list one by one. Alright, so I'll show you that code, but that code will help us to basically reduce the type space complexity to of one, as we are not storing anything. We are just rearranging these elements. So let's say we want to combine two lists. All right. So we'll make a new function because that's the repetitive part to compare two linked lists, right? So we'll make a function for merge, okay, in which will basically pass to list node. All right, list node L1 and list node L2. And here we obviously have n number of lists, so we need to apply a for loop and basically take the list one by one and update the previous list, right? So uh, because we have, let's say, L1, L2, L3, L4. So we'll apply the merge function on this two list and make a new list. Next, we'll apply the function on this two list. We'll make one more list. Next, we'll apply the function on these two lists and make one more list. So, and this list will be our final list, which will contain all the elements in sorted order. Alright, so if you can see, we are basically doing the iteration for each and every list. Alright, combining each and every list. So obviously, time complexity will be more fine. Let's start the code. So let's consider all the lists one by one. Alright, so we'll consider I equal to I equal to 0. I should be less than the list of length and increment the value of list. And so list of, we can say I equal to, will pass the list to a function merge that we have created, right? So inside this, I'm not adding the s. Okay, sorry. I could have s. Right, so this will be combination of I and obviously I plus 1, right? Combination of I that is 0 plus 0, 1, 2. So we are combining the first and second list, and now this list will come at the index 1 position, that is I plus 1. So that's the reason we have to make this actually I plus 1, and we'll pass the list, and this will give us the new list, right? So at the end, obviously the last list, right? So 0, 1, 2, 3, and the third list at the index position 3, that is list of 3 will contain the final list, right? So obviously we have to return the last list, that is list dot then minus 1 list. That will be our answer. So we'll write the code for combining the two lists. All right. Okay. So we'll first perform the while loop to traverse the list. Okay, we'll check L1 should not be equal to null, and also L2 should not be equal to null. Then only obviously we can traverse the list, right? Once we have checked this inside it, now we'll check for the values of L1 and L2. So if L1 dot value is less than or equal to, let's say, L2 dot value, then obviously uh, we can consider that node, right? So, but before that, we have to obviously consider the dummy node, right? Which will point the uh, which will keep track of the head of the uh, list that we are creating, right? So the dummy will be um, equal to new. this node and 0, let's assign it 0, and also we need a current pointer, alright, which will point to dummy node, but this current will move one by one to the new node. So, alright, so L1 is less than L2, right? So we can do, so we can do, um, okay, okay, so else we'll go here, and obviously, so L1 equal to L1 dot next, so we have to move the to the next node, and here obviously L2 equal to L2 dot next. But while doing so, we also have to consider that value current dot next equal to L1, right? And here as well, we have to current dot next equal to L2, right? And obviously after that, we have to move the current pointer forward. So current equal to current dot next, all right? So this function will make sure that we are basically um, traversing the whole list, all right? And once so after one list has ended, let's say there are there are three elements in this list, and let's say there are two, that is only one element. So once we once L1 is here, L2 is here, now L1 will move over here, L2 will move to the null pointer. All right. So after that, obviously, we still have to consider these values, right? The remaining values of the list one. So for that, we'll check which of the two lists are actually not null. So if L1 is not null, then obviously we'll do current dot next equal to L1, and same logic will apply for L2 as well. So if L2, let's say L2 is not null, then current dot next equal to L2, and we'll return the dummy dot next, since dummy variable is always pointing to the head node, right? The current variable is always moving, right? But the dummy, that is this variable, is always pointing to the head. That's the reason we on the first place we have taken the dummy node. So we'll return the dummy dot next, alright, to here. And let's just run and check for any syntax error, then we'll modify our code. Yeah, all right. Okay, so we haven't added the return type. So return type will be uh, list node, right? Okay, so it's list. Okay, in array index out of bound. All right. So what's the error? Let's see. Oh, okay. So it should be list of length minus one, because we are not going to actually list of minus one out of bound. Okay. Um, an index out of bound, index minus one out of bound. Oh, okay, okay. So when there is blank list, it's giving error, right? So if it's blank, let's say here only we can add, if let's say list dot length, it's not length, list dot length is, or in fact list, if we can do directly do uh, list is equal to null, then we can just return return blank list, right? So maybe we can return null, I guess. Let's see, because list of length. Okay, so maybe we can just add something like this. list total length equal to null. Okay, type binary. Oh, sorry. So list of length can't be null. It should be zero, right? My bad. Then we can return null value. Okay, let's check for all the other test cases. Okay, so it's working properly. Okay, so we have, so as I told before, so the space complexity of this will be of one, right? Because we are not creating any new nodes, we are just rearranging the existing nodes. And the time complexity of, so the space complexity is O of one. And the time complexity for this will be, let's see. Oh, obviously, we are traversing the whole list length, right? So, um, all right. So there are key list, and we are traversing all that, and the merge part is traversing all the n number of um nodes, right? So if this part will obviously take O of n, right? Right, not this part, but the whole merge part, and this will take k times because let's assume there are k lists and there are n number of total nodes among k lists. Okay, this is the total nodes. This n is the total node. So our time complexity will obviously be k lists, right? We'll be considering k lists and the merge thing, the merge function will take n, consider n number of nodes for k lists, so it will take O of k into n. I hope that's correct. And so it's working properly for all the other cases. All right. But there's even a better approach than this. So right now, well, we have done this thing, right? Just focus on this thing. So we are basically combining the list uh, one by one, right? L1, L2. But why do we need to combine that one by one? We, if we have done merge, if you have ever come across merge sort, right? So merge sort basically works on the principle of divide and conquer. All right, merge sort. All right, so what's divide and conquer? So we'll be combining, we'll be using the same merge function for combining two lists at one time, right? Because we can't, it's difficult to combine three or more lists at one time. Rather, we'll stick to the two combined two lists. But when this combination is happening, and these two lists are combining, this L3 and L4 are actually waiting for that to be taken, right? And let's say there are key number of lists. While this thing is happening, why should all the elements in the list should wait, right? So rather what we'll do is we'll combine by set of pairs, right? Because we can combine maximum two lists. So we'll combine these two lists, we'll make one more list. At the same time, we'll also combine these two lists and we'll make one more list. Alright, so now this will be list one, this will be list two. And now we can combine both the lists and make our final list. So if you see properly, first of all, we are reducing the number of iterations that we are calling the merge function, right? Because this will take 1, 2, 3. So we have already taken the complexity for this also k into n. But this, if you have done binary search, right, this will drastically reduce the number of, we can say, time by half, right? Because here we are considering 2 raised to 4 list. Here we are considering 2 raised to 1. Here we got the final list that is 2 raised to 0 that is actually 1 list. Alright, and next there are k number of lists, so it will take 2 of 2 raised to k. Alright, so let's say if we have k number of lists that we have to combine. So, so basically our main goal is to divide the 2 raised to k such a way that will reach uh, what basically we have key list, alright, and we have to divide the key list. So how many times that will reach one, right? Our goal is to reach one, the final list, and we have to basically divide by x number of times. We have to divide the key two times for how many times until we reach one. So that's the main question, right? So x, find x, right? So if you have an algebra part, so k equal to x is a simple algebra. Let's apply to these two from these sides. Alright, so after the is equal to these two of k and l becomes after the base two of base two x. And if you have done logarithmic properties, so if you have constant, say log of k to the base k, and let's say we have n here on the exponential part, so this answer will obviously be x. So the output for the right hand side will be x, and on the left hand side we don't have to actually consider the space too, right? We can just ignore it, and this becomes x equal to log k. So basically we have reduced the number of iterations from k to log of k, right? Just and obviously log of k is far better than k, right? When we have a large number, extra large number of less than this log of k will be very challenging. Alright, so this definitely will help us a lot. Obviously, the space complexity here will also be overwhelmed as we are not changing the actual logic, we are just modifying basic logic to work more efficiently, right? So, so the auto complexity the time complexity for this part will be O of n from so n obviously that covers the whole list and all the cases because the first function that we are applying for combining both the list should have all the nodes. So obviously it will be n, but the second part of what I was saying list will drastically reduce by log k. So that's even better time complexity than the previous one. So so let's actually start applying the logic. So we can do it in the recursive pattern. So this part, that is the merge function, will remain the same because well we are actually combining these two lists at a time, right? So the part that will be changing is this merge the sorted part. So we can do it by a recursive function or recursive function call, right? Um, so this part will kind of remain the same and will basically define a new function, right? That will be the divide part. Okay, this will help us to basically divide the list into smaller groups, and those groups we can further give it to the merge function. All right, so for dividing, we'll obviously give the list node, right? um Also give the left integer and the right integer. That will be help us to pointing the uh, uh, left and right limit of their list, right? And we'll be basically dividing the list, all right? So let's say there is one L and this is one R, right? We'll find the mid. That's the mid right over here. So now this is L and M will be our one list, and M plus one, that is two, and R will be our second list, right? That we will divide the list. And for let's say key list also, this logic will remain the same. Here, uh, we'll check first. We have to do the recursion. We'll do it in a recursive way. So we'll first check if L is greater than R, then obviously we have to terminate. right? We just have to return the list. And obviously that will be a list, right? And here we'll call the divide function, right? And this we can basically give the list of the list, and the left will be obviously 0 and right will be the actual length of the list, that is list of length minus 1. All right, and so now let's continue with our list divide function. And if let's say L is equal to R, like, right, that means there is only one list. So we'll just have to return that list as it is, right? Return the list as it is. Now we'll actually start the division part. All right, so we obviously have to calculate the mid, right? So let's calculate the mid. L plus R minus L by 2. All right, and once mid is calculated, then we can find the left and right part. So 1 divided for left, 1 divided for right. So inside here we'll pass the list. All right, the left edge will be 0 to mid, and for right that will be mid plus 1 to R. All right, and once you have divided it, obviously we have to store it, right? So we'll store it um, in a list node, let's the left, and same will do for the right as well. All right, and now obviously this two lists should go to the merge function for combining, right? So we'll call the merge function. Merge will return the value, right? So merge will return the value directly, merge, and list 1 and list 2. So list are left and right. So lists are list left and list right. And okay, so and then at the end, okay, so obviously we are returning the list value, right? So it will be list node, and this obviously will be our final list. So let's do something like this. We'll directly return the value from the divide function. That will be our final list that we're passing through the merge function. So let's check for any syntax error. Okay, so cannot find symbol ln. Okay, so because it's, let's define it something like this. Okay, incompatible type. All right, so okay, got it. So if L is greater than R, that means obviously we have traversed a whole list, right? So we'll just define, so we'll just return null. Let's check again. Okay, so cannot find symbol list. Okay, okay, because it's list mentioned here. So let's just check once. Passing list here. It's getting here. It will be S. Okay, right. Let's check again. Okay, so it's that means the syntax is proper and working for the basic test cases. Let's check for all the other cases. Okay, so time limit exceeded. Oh, so we found the error. So the error part was here in the divide part. So I've taken 0, but actually it should be L, right? Because this part is L and this is M. So ideally it should be L and not 0, right? That was the error part. Okay, so now it's working properly. It's submitted. Yeah, so it's working properly, and this is definitely a better code. Yeah, so the L should obviously be changing, right? In every pass, we are actually passing 0 always, and that's the reason the list is basically going to a recursive part. It's not actually updating the proper value of L. That's why it's not moving forward and it's just considering the list over and over again. So that was causing the error. Just a small correction. So as I told before, so this time complexity will be O of n into log n, right? Well, n is the number of total nodes and log k will be obviously k is the number of list and log k is because we are kind of dividing the whole list pairs divided by 2, right? And so I said the space complexity will be O of 1, but it's not exactly O of 1 because if you see at each level, right, we are actually storing the list and inside a left and right array, right? And then we are using the same list for the next merge function and we are passing it to the next array. So it will be basically the total number of times we are basically uh, calling that merge function, that is simply log of k, right? And that's the reason the space complexity for this approach will be O of log k, right? I will discuss one more approach. So let's go here. So initially we are given three lists, right? So initially we are given L1, L2, and L3. There are three lists. We have to combine these three lists. So what we were doing is combining these two lists, okay, and then passing the resultant list to the third list, or we are basically making pairs. But what if we consider, let's say this is not a list and this is an array, right? And then we can actually use three variables like I, j, k, and we can compare all these three elements together, right? Because these lists are in a sorted ascending order. That means the first element will be always smaller. So you can just compare all these three elements which is smaller, that is one. So make one, then we will move the pointer for, let's say L, we consider L1. So the now L1 will move over here. Now we'll consider all these three lists simultaneously. That is L1 with this one and this two. So now initially we'll add one, then we'll add one from this. So now it will move over here and combine again this three. Now this two is smaller than this two will now go to here and three. Now we'll consider three and then move this L2 to here. So this approach we can't do this because we don't have key number of we have to do the loop key number of times, right? So what can be done to to use the same concept that we are using here, but rather with an efficient way to find the minimal element, right? So we can use the concept of priority queue, or we can say minimum heap and maximum heap. So minimum heap can be used to basically extract the smallest element, right, from the whole heap that we are storing, that, or we can say a queue, or we can say a list number of nodes that we are actually storing inside the heap, and that takes a lot of less time. And to implement that, we can use the data structure as priority queue, right? So let's see how to implement this, and then we'll see what's the space and time complexity for it. All right. So firstly, I'll just define the priority queue. Right, let's name it as min heap. Alright. And inside this will be obviously storing list nodes, right? And in the bracket now we'll mention something like this: a comma b arrow a dot well minus b well. So this basically gives us the minimum heap. If we want maximum heap, then we just have to write b dot well minus a dot well, and that will basically us arrange all those nodes in the descending order. It doesn't do it automatically. We just have to initially, do the for loop and add those nodes one by one. So we'll consider all the nodes from the list, right? So this alone will take O of key, right? So we'll firstly check if the list is not equal to null, then only we'll add it into the min heap, right? So we'll add it to the min heap and min heap dot offer. So it's similar to priority queue. So we'll use the same function that we're using inside the queue, that is offer, to add the element inside the queue, and we'll offer list. Alright, now this will repeat until we have basically uh, added all the elements inside the heap. That means we'll add all those elements inside this, right? So our queue, so let's consider the same. We can say example 1451346. Consider the same similar example. You have these three lists, and let's say we have a queue. Let's say this is our priority queue, all right. And initially we'll add all these three elements inside the queue. That is one and two, right? And obviously this will be having the exact address, so it won't, so it's easier to identify that this one belongs to this list and this one belongs to this list. So we don't have to worry about that. And now we will basically extract what's the minimum element from the priority queue, and that's obviously one. So either it can be this or this, doesn't matter. It will be same, and then we'll define a dummy pointer, obviously as usual, and a current pointer that will point the dummy, and then basically uh, do one, that is the first element, and we'll move the current pointer here. Then let's say we are considering this one, all right? So now we'll basically move this to the next node, and we'll add now this node inside the priority queue, and we'll basically replace the node. Let's say this node will now be replaced by 3, right? And this will obviously be sorted in the ascending order. So now whenever we are fetching the new next smallest element, it will give us 1 from this, all right? And this will come here. The current will move to the next element, and obviously this will be removed, and the next element will be added from this list, that is 4. Now we compare all these three elements, and the smallest will be 2. So we'll add the 2, right? Current will move to the next element, and then this 2 will be removed, and in the place of that, the next element in that list will be added, that is 6. The same thing will repeat for all the other elements. Now 3 will be smallest, then after that 5 will be added. Alright, so 5 will be added in place of 3, and next smallest will be 4. So 4 will be added. Alright, the C will obviously be moving continuously, that is the current pointer. So, and then we'll add 5. Alright, and once the element has reached the end of the list, then we obviously don't have to add anything, right? Then this goes to 5, and then lastly, and then lastly, it will reach the sixth element. Alright, and so this will be also removed, and the once the queue is totally empty, then we can say that we have traversed all the elements from the k lists, all the n elements from the k lists, and hence the output resultant we can just put dummy dot next, and that will give us the output list that is totally sorted. So we have added the initial elements inside the list. Now we'll alright, so it'll be easier to visualize it. So now we'll use the dummy and the current uh, variable. So this node dummy will that new, and also this node current which will point to dummy. Alright, and next we'll just know while a queue is empty, we'll be checking, we'll be basically adding and removing those elements inside the queue and comparing, right? So the queue name is minimum heap. So until our minimum heap is not equal, sorry, our minimum heap is not empty, we'll just continue all the operations. So what will be the operations? So initially, we'll obviously, um, we'll basically pull, right? Pull from the heap. So main heap dot pull, and this will basically give us the smallest element, alright, and that will store inside a, let's say, a node, list node, alright, and obviously this will be the smallest element. So so um, we'll do current dot next equal to node. That way, a current will actually point that node, alright, and we have to obviously move that node to the next element, right? So we'll also do node equal to node dot next, alright. Now we have added that we have removed that element that we have pulled, but instead of that, at the same time, we also have to add the new element that we have considered inside the queue, right? So we just have to check whether the node is not equal to null, and if it's not equal, then we can obviously add that node inside the um, minimum heap or the priority queue, right? So minimum heap dot offer, we can add that node inside the, and so that's the basic part. And after that, obviously, at the end, once everything is over, we can just return the dummy dot next will be pointing, which will be pointing to the head value. All right, let's just check for any syntax error. Okay, okay, so I guess we haven't added the brackets, right? So it's a syntax error. So let's just check again. So okay, so it's working for this. So okay, let's see. Because it's not okay. Oh, okay, because we are not moving the current, right? That's the reason it's not showing top. So current equal to current dot next. That way it will traverse the same all the other elements. So we were actually not adding the element inside the list. Okay, so it's working properly. I updated the current as well. Let's check for other test cases as well, and then let's see the complexity. Okay, so it's working properly. So let's see for the space and time complexity. Right. So obviously the space complexity, since we are storing all these nodes inside the queue, right? The n number of nodes. So the space complexity will take off n due to the minimum heap, and the time complexity will be, so there are n elements, right? And n elements we are going to add inside the queue, right? So this part on its own will take off k, right? And then this part, since the queue is not empty, then we have to run this part for O of n time because we have to poll each element, right? So it will be minimum that will be O of n. Okay. And so this will take n times, right? And the actual, we can say the adding the element, that is the operations of any priority queue, takes log of how many elements are present inside the queue. So there are k elements present at a single point of time. So it will take log of k times. And these operations will be applying for n number of times until the queue is empty. So that's the reason time complexity will be O of n log k. And obviously, this is the same complexity that we are getting in this merge. So that is divide and conquer. The space complexity here was log of k, whereas here it's log of n. So obviously, this approach is better in comparison to the space complexity point of view. But this approach is also a simple approach if you don't want to complicate things, right? So yeah, that's it for the video. Thank you for watching.